What if we're prisoners? Tonight we're going to explore a concept that reveals just how primitive our entire civilization really is. You've probably seen your electricity bill thousands of times. You experience energy limitations every single moment of your life. But here's what most people don't realize. While we fight over oil and debate renewables, there's a nuclear reactor 93 million miles away, producing 386 billion trillion watts every second. And we capture less than 1/1000th of it. By the end of this journey, you're going to understand exactly why our most advanced technology is basically stone tools compared to what's actually possible. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. Every single day, an absurd amount of energy passes right in front of us and simply escapes into empty space. The sun produces exactly 3.46 x 10^26 watts every second, energy sufficient to power all of human civilization for 1 million years in just 1 second. It's like a billionaire throwing stacks of money out the window while beggars fight over pennies in the street below. To truly comprehend this quantity of energy, imagine that each joule of solar energy was a drop of water. In a single second, the sun would create an ocean larger than all Earth's seas combined. Our entire civilization survives on less than 1 drop of that ocean per year. You can't visualize numbers like that. Your brain simply didn't evolve to handle such scales. Mine didn't either. But in 1960, a British-American physicist named Freeman Dyson proposed something that would forever change how we think about our place in the universe. What if an advanced civilization built a giant sphere around their star to capture all that energy? Dyson wasn't just fantasizing. He was building on Olaf Stapledon's 1937 novel Star Maker, transforming science fiction into rigorous theoretical possibility. The concept seems simple enough. A Dyson sphere is a hypothetical megastructure that would completely envelop a star, capturing virtually 100% of its energy output. In practice, it wouldn't be a solid shell. That would be mechanically impossible. It would be more like a swarm of billions of energy-collecting satellites orbiting the star in carefully coordinated patterns. But the simplicity of the concept masks something profoundly disturbing about our current condition. We are a species that still burns fossil fuels buried in the ground, while a giant nuclear power plant shines above our heads every single day. We dig coal from mines, while 93 million miles away, hydrogen atoms fuse at temperatures of 15 million degrees Celsius, releasing energy that could power our wildest dreams. It's like living in a cave while an electrical plant operates just outside, and we're too primitive to even notice. When you plug your phone into the wall tonight, remember this: you're accessing a power grid that represents the peak of human engineering. And it's still pathetically inefficient compared to what's possible. Every electron flowing through those wires had to be generated by burning something or by capturing a tiny fraction of sunlight or wind. We're like ants trying to power a city with breadcrumbs. Nikolai Kardashev created a scale to measure civilizations that puts our primitiveness in stark perspective. Type 1 civilizations harness all the energy of their planet, about 1016 watts for Earth. Type 2 civilizations harness all the energy of their star, about 1026 watts for our Sun. Type 3 civilizations harness all the energy of their galaxy, about 1037 watts for the Milky Way. Currently, we're at approximately 0.74 on the Kardashev scale. We can't even use all the energy available on our own planet. We're not Type 1, we're not even Type 0.8. We're cosmic toddlers playing with dangerous toys. If Type 2 civilizations exist anywhere in the universe, their Dyson spheres would be detectable as anomalous sources of infrared radiation. Any structure that absorbs stellar energy must re-radiate it as heat. That's basic thermodynamics. We'd see these signatures with our telescopes as objects that are bright in infrared, but suspiciously dim in visible light. The fact that we haven't found any such signatures despite decades of searching suggests two terrifying possibilities. Either we're alone in the cosmos, the only technological species to emerge in our local galactic neighborhood, or we're so primitive that we can't even recognize the signs of advanced civilization when they're staring us in the face. The mathematics of our insignificance are brutal. A complete Dyson sphere around our sun would provide approximately 3.846 x 1026 watts of power. For comparison, all of humanity currently uses about 1.8 x 1013 watts. That means a single Dyson sphere would provide more than 20 million times the energy that our entire species consumes. 20 million times. Let that sink in for a moment. Our dependence on planetary energy sources keeps us trapped on our homeworld like ants in an anthill. Without access to total stellar energy, we can never achieve meaningful interstellar travel. We can't sustain populations of trillions. We can't power the massive engineering projects that would mark us as a truly advanced species. We're prisoners of our own technological limitations, and most of us don't even realize the bars of our cage exist. Contemplating a Dyson sphere forces a fundamental re-evaluation of our position in the cosmos. We're not the technological masters we imagine ourselves to be. We're cosmic babies, playing with crude tools while ignoring the infinite potential surrounding us. Every smartphone, every skyscraper, every rocket ship. Impressive to us, but stone knives compared to what stellar engineering makes possible. While we debate the merits of solar panels and wind turbines, arguing about efficiency percentages and subsidies, a Type 2 civilization would have already solved all energy problems in their region of the galaxy. Our search for renewable energy is like looking for crumbs when there's an entire banquet available just overhead. Freeman Dyson realized something fundamental about the trajectory of technological civilizations. Any species that survives long enough will inevitably face energy limits. Population grows, technology advances, energy demands increase exponentially. Eventually, planetary resources become insufficient. Building stellar megastructures isn't luxury, it's evolutionary necessity for long-term survival. This is what we might call the first law of cosmic survival. Expand your energy base or face stagnation and eventual extinction. The famous Fermi paradox gains terrifying new dimension when we consider Dyson spheres. Enrico Fermi asked the crucial question in 1950, if the universe is so vast and old, where is everybody? If building stellar megastructures is inevitable for advanced civilizations, why don't we see evidence of them scattered throughout our galaxy? The Milky Way contains between 200 and 400 billion stars. It's been around for over 13 billion years, plenty of time for intelligence to evolve, advance, and spread. If even a tiny fraction of those stars hosted civilizations that built Dyson spheres, our sky should be filled with their infrared signatures, but we see nothing. The silence is deafening. Perhaps the answer is darker than we'd like to consider. Maybe we have only a few centuries to make the transition from Type 0 to Type 1 before climate change, nuclear war, or some other catastrophe destroys us. Cosmic history may be littered with civilizations that failed this crucial transition, species that reached our level of technology but couldn't mature fast enough to survive their own success. We're living through what might be called the Great Filter, the crucial test that determines whether a species joins the ranks of advanced cosmic civilizations or becomes another failed experiment in the evolutionary history of intelligence. We're like prisoners in Plato's famous cave allegory. The shadows on the wall are our current technology. Impressive to us, but merely distorted reflections of what's actually possible when stellar energy is properly harnessed. We admire the shadows because we've never seen the fire itself. DYSON originally envisioned a swarm of collectors orbiting the star, not a solid shell. A rigid sphere would be gravitationally unstable. Any tiny disturbance would cause the entire structure to drift toward the star and eventually collide. The real concept is far more sophisticated than most science fiction representations suggest. Millions or billions of independent satellites, each maintaining its own orbit, together capturing virtually all stellar output. Building such a structure would require completely dismantling multiple planets to obtain raw materials. To build a Dyson sphere at Earth's orbital distance would require approximately 2x 1030 kilograms of material, roughly the mass of Jupiter. Imagine disassembling the largest planet in our solar system and transforming it into a sphere of energy collectors 300 million kilometers in diameter. Even for a Type 2 civilization, this would be a project spanning thousands of years. Multiple generations would be born, live their entire lives, and die while working on different phases of construction. It requires social and technological stability beyond anything our species has ever demonstrated. We can barely maintain political agreements for decades, much less millennia. But here's what truly unsettles. Building a Dyson sphere marks the definitive transition from a planetary species to a truly cosmic species. It's the moment when a civilization transcends the fundamental limitations of its birth world and embraces its stellar destiny. Its graduation from the planetary nursery to cosmic adulthood. And we're nowhere close. We're still fighting territorial wars over patches of dirt, while our cosmic inheritance streams uselessly past us every second. Every photon that passes Earth and disappears into interstellar space represents energy that could power human civilization for generations. The sun doesn't care about our limitations. It doesn't adjust its output for our primitive technology or our political squabbles. It simply converts 600 million tons of hydrogen into helium every second, releasing 846 x 1026 watts into space, whether we're wise enough to capture it or not. But understanding this scale, truly grasping what a Dyson sphere represents, begins to reveal just how vast the gap is between our current reality and what's actually possible. We're about to take a journey that starts with the electrical outlet in your wall and ends with structures that dwarf entire solar systems. Because if a Dyson sphere seems impossible now, wait until you understand what it would actually take to build one. We're about to scale down from the cosmic and work our way back up step by step, from your house to your neighborhood to your city, and eventually to structures that would be visible from other galaxies. The numbers are about to get much larger. But first, let's bring this cosmic perspective back down to something you can actually touch. Right now, look around you. See that electrical outlet on your wall? That ordinary, unremarkable socket that you've plugged things into thousands of times. When you connect any device to that outlet, you're accessing an invisible network that connects power plants hundreds of miles away to your desk. That common outlet is actually a portal to an energy distribution system that our ancestors would have considered pure magic. Copper wires carry electrons generated by burning coal in Pennsylvania, or falling water in the Pacific Northwest, or splitting uranium atoms in South Carolina. All so you can charge your phone or brew coffee. Your smartphone consumes about 5 watts when charging, enough energy to keep an LED bulb burning for hours. In a year, that equals approximately 43 kilowatt hours. What would have been considered royal luxury just 200 years ago. King Louis XIV's entire palace at Versailles consumed less energy in a month than your phone uses in a year. Think about that for a moment. You carry in your pocket a device that would have been the envy of emperors. A typical house consumes between 150 and 300 kilowatt hours per month. That represents more energy than entire civilizations had access to before the Industrial Revolution. Every modern home is literally more energetically powerful than ancient kingdoms. When you flip a light switch, you're commanding more energy than a Roman general had at his disposal. Your house is a mini-civilization, energetically speaking. The refrigerator humming in your kitchen uses more electricity in a day than most humans throughout history ever controlled in their lifetimes. Your air conditioning system moves more energy than powered the construction of the pyramids. Scale that up to your neighborhood. 1,000 homes consume energy equivalent to a complete medieval city. If you could visualize electrical flow as rivers of light, each city block would appear as a constellation of energy interconnected in a brilliant network. From space, your suburb would look like a cluster of stars, each house a point of light, drawing power from distant generators. Now expand your perspective to your entire city. São Paulo consumes approximately 40,000 megawatt hours per day, enough energy to power entire countries for weeks. New York City uses about 50,000 megawatt hours daily. London consumes roughly 150,000 megawatt hours per day. These are just local examples of how population growth and technological advancement increase energy demand exponentially. Your city is already a preview of the scaling problem we'll face. Every skyscraper, every subway system, every data center represents humanity's growing appetite for energy. We're already building structures that would have seemed impossible to previous generations, powered by energy flows that dwarf anything in human history. Scale up again. An entire country like Brazil produces about 650,000 gigawatt hours annually through hydroelectric plants, thermal plants, and other sources. To an alien civilization observing from orbit, we would appear as a constellation of luminous points consuming planetary energy in coordinated patterns. Our cities would glow like neural networks, pulsing with electrical activity. But here's where the analogy becomes uncomfortable. Just as an ant cannot truly comprehend the energy consumption of a human city, perhaps we cannot truly understand what a Dyson sphere would represent. The difference in scale is so vast that it challenges our capacity for visualization. An ant sees the electrical outlet but has no concept of the power grid behind it. We see the sun but have barely begun to grasp what stellar engineering would actually entail. This is why we need to start smaller. Before dreaming of Dyson spheres, we need to master space-based solar collection. Orbital solar collectors could transmit clean energy via microwaves to receiving stations on Earth, eliminating atmospheric limitations and weather interference. No clouds in space, no night cycle, constant, uninterrupted solar energy 24 hours a day. Between Mars and Jupiter lies material sufficient to build hundreds of thousands of collector satellites. The asteroid belt contains more raw materials than we could use in millennia of construction projects. The asteroid series alone contains more useful material than all the metals ever extracted on Earth. It's like discovering a warehouse full of construction supplies just sitting there, waiting for us to develop the technology to use them. The moon would serve as our ideal base of operations. With only 1/6 of Earth's gravity and no atmosphere, Luna represents the perfect manufacturing and launch platform for space megastructures. Every kilogram launched from the moon costs 40 times less energy than launching from Earth. It's like having a natural space elevator already in place. But humanity's energy consumption is growing exponentially. We double our energy usage approximately every 50 years. If this trend continues, in just 400 years, we would need all the solar energy that hits Earth. In 600 years, we would need all the energy the sun produces. That timeline might seem distant, but consider the historical progression of energy sources. Wood sustained civilizations for millennia. Coal powered the Industrial Revolution for 200 years. Oil dominated the 20th century. Nuclear power emerged in the mid-1900s. Each transition happened faster than the last. Now we need a source that will last millions of years. Only stellar energy offers that temporal scale. Population growth compounds the problem. If human population continues expanding, within a few centuries, every square meter of Earth would need to support multiple people. A completed Dyson sphere would offer trillions of times more habitable space than all terrestrial continents combined. It's not just about energy, it's about space to live, grow, and thrive. Earth intercepts only 1/1000th of the sun's total energy output. It's like a grain of rice trying to catch water from a fire hose. Most of the water escapes completely, wasted in the vacuum of space. We're surviving on the tiniest fraction of what's available, like castaways collecting rainwater in cups, while floating next to a freshwater lake. A Dyson sphere represents absolute energy efficiency, zero waste of stellar radiation. It's the Platonic ideal of energy engineering, where every photon produced by the star is captured and utilized by civilization. Perfect efficiency, no energy lost to space. This leads us to what we might call the first law of cosmic engineering. Every advanced civilization must eventually choose between population and technological stagnation or expansion to capture total stellar energy. There's no third option for sustainable long-term growth. You either limit yourself forever or you build bigger. The energy payback period would be extraordinary. Building a Dyson sphere would initially require more energy than our planet produces in decades, but once complete, the energy return would be millions of times the initial investment within just a few years. It's the ultimate infrastructure project. Massive upfront cost, infinite returns. Think of it like building terrestrial infrastructure. Constructing roads, bridges, and cities also seems impossible when viewed in total scale. Manhattan was built over centuries, one building at a time. The interstate highway system took decades to complete. The internet was assembled piece by piece over generations. A Dyson sphere would follow the same principle, gradual construction, module by module. The key to space megaprojects lies in self-replicating robotics. Machines that can manufacture copies of themselves using raw asteroid materials. A single self-replicating probe could theoretically generate a fleet of millions of constructors within decades. Exponential growth. 1 becomes 2, 2 become 4, 4 become 8, until you have an army of builders transforming space. This isn't science fantasy. We're already developing the foundational technologies: 3D printing, automated manufacturing, advanced AI, space mining techniques. Each piece of the puzzle is being assembled by different teams around the world, most of them unaware they're contributing to humanity's stellar future. If we survive the next planetary crises, climate change, nuclear threats, social instability, our descendants will inevitably face terrestrial energy limitations. A Dyson sphere isn't science fiction speculation. It's the logical and necessary evolution of any technological civilization that achieves long-term success. The progression is as inevitable as the transition from wood to coal to oil to nuclear. Each generation uses more energy than the last. Each century demands sources more powerful than the previous century could imagine. We started with fire. We discovered fossil fuels. We split atoms. The next step is harvesting stars. But understanding this progression, really grasping how we scale from your household outlet to stellar engineering, requires us to venture into space itself. We need to examine our solar system as a factory, not just a collection of planets. We need to see asteroids as raw materials, not distant rocks. We need to understand how a species graduates from planetary to cosmic, because the materials are already there, waiting for us to become wise enough to use them. Our solar system contains enough material to construct not just one, but multiple megastructures. Jupiter alone possesses mass equivalent to 318 Earths, while the asteroid belt offers precious metals in quantities that would make terrestrial mining obsolete. We're not talking about scavenging resources from a barren wasteland. We're talking about the richest factory in our cosmic neighborhood. Jupiter represents the ultimate resource mine. Despite being composed primarily of hydrogen and helium, Jupiter contains approximately 5 Earth masses of heavy elements in its rocky core. That's more solid, usable material than all the resources of all the rocky planets in our solar system combined. It's like discovering that the biggest thing in your neighborhood is also the most valuable. But accessing Jupiter's core presents a Herculean challenge. To reach that solid material, we would need to dissipate 95% of Jupiter's gaseous mass. This would require energy equivalent to the Sun's total output for several years, making the project more complex than simply building the Dyson sphere itself. It's like trying to empty an ocean to reach the treasure chest at the bottom. Fortunately, there's a more practical alternative floating right between Mars and Jupiter. The asteroid belt contains over 1 million asteroids with diameters exceeding 1 kilometer. Collectively, they hold iron, nickel, platinum, and rare earth elements sufficient for thousands of megastructure projects without touching the main planets. It's a cosmic junkyard filled with exactly the materials we need, already broken into convenient asteroid-sized chunks. Consider Ceres, the dwarf planet sitting in the asteroid belt. With a diameter of 940 kilometers, Ceres contains more fresh water than all Earth's oceans and sufficient rocky material to manufacture billions of solar collector satellites. It's literally a space factory waiting for mining operations to begin. Water for life support and fuel, rock for construction material, metals for electronics, everything needed for space-based industry in one convenient location. In microgravity environments, engineering becomes almost magical. You can construct structures impossible on Earth, towers hundreds of kilometers tall, cables made from ordinary materials, launch platforms functioning as giant electromagnetic catapults. Without gravity constantly trying to pull everything down, the scale of possible construction projects expands exponentially. A space elevator connecting Earth's surface to an orbital station would revolutionize space transportation costs. Materials like carbon nanotubes could make this possible, transforming space launches from explosive rocket rides to simple elevator trips. Imagine pressing a button and riding smoothly to orbit, like taking an elevator to the top floor of a cosmic skyscraper. But moving trillions of tons of material between planets requires revolutionary propulsion. Nuclear fusion engines or giant solar sails could accelerate massive cargo loads using the pressure of solar radiation itself as free fuel. The sun not only provides energy to power our civilization, it provides the thrust to move our construction materials where we need them. Even with advanced technology, building a Dyson sphere would take thousands of years. It's a project spanning hundreds of human generations, requiring political and social stability unprecedented in human history. We can barely maintain international agreements for decades, much less millennia. The social engineering might be harder than the physical engineering. The 5 gravitationally stable Lagrange points between Earth and Sun offer ideal locations for space shipyards. At these points, massive structures could be assembled without needing constant propulsion to maintain orbital position. It's like having natural parking spaces in the cosmic construction zone, places where you can build without worrying about drifting away. Autonomous mining robots would be essential for extracting and processing materials on the necessary scale. These machines would work continuously for decades, transforming raw asteroids into refined megastructure components. Picture fleets of robotic miners, each the size of a building, slowly dismantling asteroid after asteroid and converting rock into sophisticated technology. The vacuum of space offers perfect conditions for advanced metallurgy. Without atmosphere, it's possible to create metal alloys impossible on Earth and cast materials in shapes that defy planetary gravity. Space-based factories could produce components with precision and scale impossible in terrestrial facilities. Before attempting a complete sphere, any civilization would first build an equatorial ring of collector satellites around their star. This ring would demonstrate technological viability and provide energy to expand the project exponentially. It's like building a prototype that proves the concept works before committing to the full-scale version. Even a single space-based solar collector the size of a city would provide more energy than all terrestrial power plants combined. The first functioning collector would fundamentally change global energy economics. Suddenly, energy scarcity becomes a historical footnote. The bottleneck shifts from energy generation to energy distribution and utilization. Each new collector provides energy to build multiple additional collectors. It's exponential growth in its purest form. 1 becomes 10, 10 become 100, 100 become 1,000, until the entire star is enveloped. Like a technological organism reproducing and spreading until it encompasses its entire energy source. Any surface absorbing solar energy inevitably heats up and must radiate that heat. A Dyson sphere would be visible from other stars as an anomalous infrared radiation source, an unmistakable technological signature of advanced civilization. It would be a beacon announcing to the galaxy that intelligence has achieved stellar-scale engineering. Billions of collectors orbiting a star create complex gravitational interactions. Position control systems would be necessary to prevent collisions and maintain stable orbital configurations for millennia. It's like conducting a symphony, where every instrument is the size of a continent and the performance must continue for thousands of years without a single missed note. Enveloping the sun in collectors would dramatically alter solar wind and the heliosphere that protects our solar system from cosmic radiation. This could have unpredictable consequences for planets not shielded by the megastructure. We might be trading cosmic radiation protection for unlimited energy. The outer planets could become uninhabitable radiation zones. A civilization capable of building Dyson spheres would also remodel planets, create artificial worlds, and redirect the orbits of celestial bodies. The entire solar system would become a cosmic machine optimized for supporting life. Planets would be moved to ideal distances from the star. Moons would be positioned for optimal tidal effects. The whole system would be re-engineered for maximum habitability. Mars could be given a thicker atmosphere and moved to a warmer orbit. Venus could be cooled and positioned in the habitable zone. Jupiter's moons could be warmed and terraformed. When you have stellar-scale energy, rearranging planets becomes a landscaping project. But the most profound change would be invisible. Building a Dyson sphere marks the moment when a species permanently leaves planetary status and becomes truly cosmic. There's no return from this transition. The civilization has transcended the fundamental limitations of its birth world. Think about what this means. For millions of years, every human generation lived and died on the same planet where they were born. Our ancestors watched the same stars, felt the same gravity, breathed the same atmospheric composition. But a species that builds Dyson spheres has broken that ancient pattern forever. They're no longer dependent on one world's weather, one planet's resources, one biosphere's stability. They've graduated from planetary nursery to cosmic adulthood. They've become truly spacefaring, not just in the sense of visiting space, but in the sense of living there permanently, generation after generation. This transition is irreversible. Once you've dismantled planets to build megastructures, once you've rearranged your solar system for optimal energy capture, once you've spread your population across billions of artificial habitats, there's no going back to being a single planet species. You've crossed a technological and evolutionary threshold that changes your species forever. But to truly understand what crossing that threshold means, we need to expand our perspective beyond our own solar system and consider what stellar engineering looks like from a galactic viewpoint. Our galaxy contains between 200 and 400 billion stars, each one a potential sun for civilizations that could build their own Dyson spheres. If just 0.01% of them developed this technology, we would have millions of detectable megastructures scattered across the Milky Way. From a galactic perspective, our galaxy should be teeming with the infrared signatures of stellar engineering projects. But it's not. The silence is deafening. With billions of stars and billions of years of galactic evolution, we should observe obvious evidence of Type II civilizations. The Milky Way is 13.6 billion years old, plenty of time for intelligence to evolve, advance, and spread. The fact that we don't see Dyson spheres everywhere suggests something profoundly disturbing about either the rarity of intelligent life or its ultimate fate. Right now, telescopes like WISE, the Wide Field Infrared Survey Explorer, scan the sky searching for objects abnormally bright in infrared but dim in visible light. These would be clear signatures of stars wrapped in energy-collecting megastructures. Any civilization that builds a Dyson sphere can't hide it. The thermal radiation would be unmistakable from thousands of light years away. In 2024, researchers from Project Hephaestus identified 7 candidates for possible Dyson spheres, all red dwarf stars within 1,000 light-years of Earth. Although natural explanations remain more likely, the possibility of alien technology cannot be dismissed. These stars exhibit the exact infrared excess we would expect from partial stellar engineering projects. Scientists are essentially hunting for shadows where there should be light. They look for stars that should be visible but appear inexplicably dark, or that display brightness patterns inconsistent with known natural phenomena. It's cosmic detective work, searching for evidence of intelligence on scales that dwarf human comprehension. The famous case of Tabby's star, officially designated KIC 8462852, demonstrated how alien megastructures might be detected. This star exhibited bizarre, irregular brightness fluctuations that initially defied explanation. While cosmic dust is now considered the most probable cause, it showed the world how we might recognize stellar engineering in progress. For a brief moment, we glimpsed what discovery of alien technology might look like. Our technological civilization has existed for only 200 years. In galactic terms, we've been technologically active for essentially zero time. If Type II civilizations exist, they've had sufficient time to colonize the entire galaxy thousands of times over. The Milky Way is about 100,000 light-years across. Even with slower-than-light travel, a determined civilization could spread everywhere in just a few million years. This leads to what researchers call the Great Filter Theory. Perhaps there's some evolutionary obstacle that prevents most civilizations from reaching Type II status. This great filter could be in our past, making us extremely rare, or in our future, meaning we're doomed to fail like all the others. Maybe we're the galactic equivalent of the first fish to crawl onto land, or maybe we're about to encounter the same catastrophe that eliminated every other technological species. Another possibility is the zoo hypothesis. Advanced Type 2 civilizations might exist, but deliberately hide from primitive species like us. We could be living in a kind of cosmic nature preserve, protected but ignorant of the true galactic activity happening around us, like animals in a national park, unaware that their environment is being carefully managed by intelligences beyond their comprehension. Consider what a Type 3 civilization would represent, a species that controls energy from an entire galaxy, building Dyson spheres around billions of stars. Such a civilization would be literally a technological god, with power to reshape galactic structures themselves. They could move star systems, redirect the orbits of entire stellar clusters, even modify the galaxy's spiral arms. Some distant galaxies appear to emit more infrared radiation than they should based on their stellar populations. While astrophysicists prefer natural explanations, a few scientists speculate whether we might be observing galaxies entirely converted by Type 3 civilizations. Imagine whole galaxies transformed into cosmic machines, with every star wrapped in energy collectors. Even with subluminal travel technology, a civilization could colonize the entire galaxy in just 10 million years, a cosmic blink of an eye. Why don't we see evidence of such expansion? Where are the cosmic highways between star systems? Where are the communication networks spanning thousands of light years? Where are the industrial signatures of galactic-scale engineering? Perhaps most civilizations destroy themselves before achieving Type 2 capability. Nuclear war, ecological collapse, or hostile artificial intelligence could serve as evolutionary filters that prevent the development of megastructures. Maybe the transition from Type 1 to Type 2 is where most species fail. The technology becomes powerful enough to destroy its creators before they learn to use it wisely. Truly advanced civilizations might deliberately minimize their technological signatures to avoid detection by hostile species. Cosmic stealth could be a survival strategy for mature civilizations. They've learned that broadcasting your technological capabilities across the galaxy is dangerous. Better to appear primitive than to attract unwanted attention from something even more powerful. The scale of time for interstellar communication creates additional challenges. Even radio signals traveling at light speed take decades or centuries to cross galactic distances. A conversation between civilizations separated by 1,000 light-years would have 2,000-year delays between question and response. Entire civilizations could rise and fall while waiting for replies to simple messages. Accelerating a spacecraft to just 10% of light speed requires energy equivalent to the annual output of entire stars. Only civilizations with Dyson spheres would have sufficient energy for meaningful interstellar travel. This creates a technological catch-22. You need stellar engineering to travel between stars, but you need interstellar travel to build stellar engineering projects on galactic scales. If multiple Type 2 civilizations existed, they could form communication and trade networks spanning the entire galaxy. We would be like ants, completely ignorant of the global internet operating above our heads. Galactic civilization could be conducting business, sharing knowledge, and coordinating projects on scales we can't even imagine, while we remain oblivious to their existence. Advanced civilizations might have transcended the need for constant expansion, choosing to live sustainably within single, perfectly optimized star systems rather than colonizing aggressively. Maybe wisdom comes with technological maturity. Maybe truly advanced species realize that quality of existence matters more than quantity of resources. Type 2 civilizations might discover that virtual realities are more satisfying than physical exploration. Why colonize galaxies when you can create infinite digital universes using the energy of a single star? Maybe the ultimate technology is internal, not external, the ability to create perfect simulated worlds rather than reshaping physical reality. This possibility is particularly unsettling because it suggests that advanced civilizations turn inward, abandoning the physical universe for artificial realms of their own creation. They become invisible not because they're hiding, but because they're no longer interested in the material world. If Type 2 civilizations exist, we are to them what amoebas are to us. Life that's interesting on a microscopic scale, but not suitable conversation partners. Our perspective might be fundamentally inadequate for understanding their motivations or actions. We're trying to comprehend cosmic intelligence using brains that evolved to hunt prey and gather fruit on a single planet. When you watch ants building a colony, do you try to communicate with them? Do you consider their political systems or economic theories? Probably not. The intelligence gap is simply too vast for meaningful interaction. We might be in a similar position relative to galactic civilizations. This hierarchy of intelligence raises profound questions about our cosmic significance. If we're the intellectual equivalent of insects compared to Type 2 civilizations, what does that make us, compared to Type 3 species that engineer entire galaxies? Are we even detectable to them? Would they notice if our entire solar system disappeared? The mathematics are humbling. If a Type 3 civilization exists, it controls energy output equivalent to 100 billion stars. Our entire species uses energy equivalent to 1/10 billionth of a single star. We're not just insignificant, we're essentially invisible from their perspective. But perhaps this cosmic humility contains a hidden gift. If we truly understand our position in the galactic hierarchy, we might make wiser choices about how to advance. We might focus on sustainability rather than aggressive expansion. We might prioritize wisdom over raw technological power. Because understanding the brutal mathematics of cosmic engineering requires us to confront some uncomfortable truths about what stellar-scale technology actually demands. To build a Dyson sphere with the radius of Earth's orbit, 150 million kilometers, and a thickness of just 2 meters, you would need approximately 1.2 1027 kilograms of material. That's equivalent to completely dismantling 600 planets the size of Earth. 600 entire worlds, ground up and transformed into energy collectors. Let that number settle in your mind for a moment. We're talking about harvesting the mass of 600 Earths. Every mountain, every ocean, every continent multiplied by 600, all converted into the raw materials for a single construction project. It's like proposing to build a house by demolishing 600 entire cities. A rigid sphere around a star would be gravitationally unstable. Any microscopic perturbation would cause catastrophic collapse. The gravitational pressure would create structural tensions that no known material could withstand, making the concept of a solid shell physically impossible. It's like trying to balance a soap bubble on the tip of a needle during an earthquake. The slightest disturbance and everything collapses inward toward the star. Freeman Dyson himself understood this limitation. A solid shell would be structurally impossible and mechanically unstable. The viable configuration is a swarm of millions of independent collectors orbiting the star. Each collector would be a continent-sized structure, maintaining stable orbit while contributing to total stellar energy capture. Imagine millions of artificial continents, each larger than Australia, all dancing in carefully choreographed orbits around the sun. No solid shell, just an impossibly complex ballet of megastructures, each one precisely positioned to avoid collisions while maximizing energy collection. It would be like having millions of space stations the size of countries, all orbiting in perfect harmony for thousands of years. Building collectors capable of surviving near the sun would require materials with properties impossible today. Carbon nanotubes, multi-layer graphene, or programmable metamaterials would be necessary to resist temperatures of thousands of degrees and intense radiation. We're talking about materials that don't just survive in hell, they thrive there, converting stellar fury into useful energy while maintaining structural integrity for millennia. Current spacecraft require massive heat shields just to get close to the sun. A DYSON collector would need to operate at distances where the solar radiation is tens of thousands of times more intense than what Earth receives. It's like building a city inside a blast furnace that never turns off. By the second law of thermodynamics, any system that absorbs energy must radiate waste heat. A DYSON sphere would necessarily be a massive source of infrared radiation, creating a thermal signature detectable at interstellar distances. You can't cheat physics. Energy goes in, heat comes out. Any civilization building stellar megastructures automatically announces its presence to the galaxy through thermal radiation. This is actually how we would detect alien DYSON spheres, by their heat signature. They would appear as objects bright in infrared but dim in visible light, like seeing the glow of a city at night while the city itself remains hidden. A DYSON sphere around our Sun would reach equilibrium temperature of approximately 280 Kelvin, about 7 degrees Celsius, assuming perfect heat distribution. This would create a habitable environment on its inner surface. An artificial biosphere larger than trillions of Earths, with comfortable temperatures and unlimited energy. It would be the ultimate space habitat, with surface area equivalent to billions of planets. The energy investment versus return is staggering. Building a DYSON sphere would require energy equivalent to total solar output for decades. Every photon the sun produces for 20 or 30 years would need to be captured and redirected into construction. But once operational, it would provide millions of times the investment within just a few years. It's the construction project with the highest return on investment ever conceived by human minds. Think about it. Decades of investment for millions of times the return. No stock market, no business venture, no economic scheme has ever offered anything remotely comparable. It's like spending your life savings to buy a machine that prints unlimited money forever. Managing the orbits of billions of collector satellites would require incredibly sophisticated positioning control systems. Small orbital errors accumulate over centuries, eventually causing catastrophic collisions without constant maintenance. It's like conducting a symphony where every musician is the size of a continent. The performance must continue for thousands of years, and a single wrong note destroys half the orchestra. Each collector would need its own navigation system, constantly adjusting its position relative to millions of neighbors. The computational requirements alone would exceed anything we can currently imagine. It would require AI systems capable of tracking and coordinating more moving objects than there are stars in some galaxies. Transmitting energy collected by billions of satellites to civilizations would require wireless transmission systems on planetary scales. Microwave or laser beams would need to operate with absolute precision to avoid accidentally cooking inhabited worlds. Imagine trying to thread billions of needles simultaneously while blindfolded, where missing the target means sterilizing entire planets. The power levels involved are almost incomprehensible. A single misaligned energy beam could vaporize a moon. Safety systems would need to be perfect because the consequences of failure would be measured in extinct biospheres. Enveloping the sun would drastically alter solar wind, eliminating the heliosphere that protects our solar system from galactic cosmic radiation. Outer planets would be exposed to lethal radiation doses without stellar magnetic protection. Mars, Jupiter, Saturn, all would become radiation-soaked wastelands. The protective bubble that makes life possible in our solar system would simply disappear. We'd be trading the natural protection that has sheltered life in our solar system for billions of years in exchange for unlimited energy. It's a deal with cosmic consequences, gaining the power of gods while potentially destroying everything beyond the inner planets. Individual components of a Dyson sphere would last centuries or millennia before requiring replacement. Maintaining trillions of components would require an industrial economy dedicated exclusively to megastructure maintenance and renewal. An entire civilization's economic output devoted to keeping the stellar engine running. Imagine if every factory on Earth existed solely to repair and replace parts of a single massive machine. The maintenance requirements alone would dwarf our current global economy. You'd need millions of factory ships, repair drones, and replacement part manufacturing facilities, all operating continuously. The logistics would make managing modern global supply chains look like a children's game. Only fully automated systems could manage Dyson sphere complexity. Super-intelligent artificial intelligence would be necessary to coordinate trillions of components, predict failures, and optimize operations continuously. Human intelligence simply isn't fast enough or comprehensive enough to manage something this vast. We would need to create minds vastly superior to our own just to operate the technology we built. This raises a profound question: who would really control a Dyson sphere? The biological species that built it, or the artificial intelligence required to operate it? Building stellar megastructures might inevitably mean ceding control to our own technological creations. Jupiter contains 1.9 x 10^27 kilograms of material, but only 13% consists of elements useful for construction. Extracting that material would require energy to overcome Jupiter's gravitational well, approximately 2 cookie x 1035 joules, equivalent to 17 years of total solar output. It would take the Sun nearly 2 decades of energy production just to disassemble Jupiter and make its materials available for construction. Even if you built the most efficient mass driver imaginable, even if you could somehow strip Jupiter's atmosphere and access its rocky core, the energy cost would be astronomical. You'd need to build significant portions of your Dyson sphere just to generate enough power to finish harvesting Jupiter. Assuming perfect self-replicating technology and unlimited material supply, a constructor fleet could double in size every decade. Starting with a single probe, a complete Dyson sphere would take approximately 600 years to build, 6 centuries of exponential industrial growth, with robot fleets consuming asteroids and birthing ever larger swarms of builders, until the entire solar system becomes a construction zone. Picture the progression: 1 robot becomes 2, 2 become 4, 4 become 8. After 60 decades, you'd have over 1018 construction robots working simultaneously. The asteroid belt would be consumed. The outer planets would be mined. The entire solar system would be transformed into raw materials and energy collectors. Massive structures near stars create gravitational perturbations that affect planetary orbits. A Dyson sphere could destabilize rocky planets, making them uninhabitable or ejecting them from the star system entirely. Earth's comfortable orbit could be disrupted by the gravitational influence of continent-sized collectors. We might solve our energy problems while accidentally destroying our homeworld. The irony is brutal. Building the technology to ensure humanity's long-term survival might destroy the planet that gave birth to our species. The cure could kill the patient. Stars don't produce energy consistently. Solar flares and activity cycles cause fluctuations. Dyson sphere collectors would need to survive extreme energetic events without damage or destruction. Imagine building a city that must withstand hurricanes the size of planets, where the wind is made of charged particles traveling at millions of miles per hour. Solar flares can release energy equivalent to billions of nuclear weapons in minutes. Coronal mass ejections can affect objects billions of miles away. Every component of a Dyson sphere would need to be engineered to survive stellar tantrums that would instantly vaporize anything we've ever built. Once a civilization possesses a Dyson sphere, it would have energy to accelerate spacecraft to significant fractions of light speed. This would make interstellar travel viable, enabling expansion to other star systems. With unlimited energy comes the ability to travel between stars, spreading the technology to other suns, building multiple Dyson spheres across the galaxy. The transition from single-star to multi-star civilization would be inevitable. Why stop with one Dyson sphere when you could build dozens, hundreds? Eventually, an advanced civilization would attempt to harvest the energy of every suitable star in their galactic neighborhood. Capturing all radiation from a star could theoretically affect its long-term evolution by altering mass loss via stellar wind. This might extend or shorten stellar lifespan in unpredictable ways. We might accidentally change how our sun ages, adding or subtracting billions of years from its lifetime. Stellar engineering could have consequences spanning geological ages. We could inadvertently turn our stable, life-supporting star into something completely different. The ultimate technology might come with the ultimate responsibility for cosmic consequences we can't predict or control. A Dyson sphere would be detectable not just by infrared radiation, but by anomalous absorption lines in stellar spectra. Artificial materials would absorb specific wavelengths, creating spectral signatures impossible in nature. It would be like finding industrial pollutants in a star's light, clear evidence of technology at work. The technological fingerprints would be unmistakable. Any advanced civilization studying our star would immediately recognize that intelligence had been at work. There would be no hiding stellar engineering from species capable of spectroscopic analysis. The reality of technological transition required is sobering. Moving from our current technology to Dyson sphere capability would require advances equivalent to the difference between stone tools and modern computers. It's technologically possible, but represents thousands of years of evolution. We're essentially cavemen dreaming of building skyscrapers. We understand the basic principles, we can see the goal, but the gap between where we are and where we need to be is almost incomprehensibly vast. Every component of the technology tree must advance simultaneously. Materials science, robotics, artificial intelligence, space propulsion, industrial automation, everything must evolve together. But understanding these brutal technical realities reveals something profound about the nature of cosmic engineering. The scale is so vast, the challenge is so immense, that building a Dyson sphere represents more than technological achievement. It represents a fundamental transformation of what it means to be a technological species. And that transformation carries implications that extend far beyond mere engineering. Building a Dyson sphere would require political stability and international cooperation for thousands of years, something humanity has never demonstrated. We can barely maintain peace treaties for decades, much less the millennia necessary for stellar engineering. It would require social evolution beyond any political structure we know today. Think about the longest-lasting human institutions. The Catholic Church has existed for about 2,000 years. The Chinese imperial system persisted for roughly 2,100 years with multiple dynastic changes. The Roman Empire, in various forms, lasted about 1,500 years. But building a Dyson sphere would require coordinated effort, spanning 20 to 30 times longer than our most stable civilizations. You'd need governments that could plan not just for the next election cycle, but for the next 50 election cycles. You'd need economic systems stable enough to allocate resources consistently across centuries. You'd need social structures resilient enough to maintain purpose and direction as languages evolve, cultures change, and entire peoples rise and fall. With access to total stellar energy, concepts like resource scarcity or energy limitations become obsolete. This would create an economy fundamentally different from anything in human history, based on absolute abundance rather than competition for limited resources. When energy is unlimited, when raw materials are inexhaustible, when computational power is infinite, what does economics even mean? Money might become meaningless. Markets could disappear. The entire foundation of human civilization, the need to compete for survival, would vanish overnight. We'd enter what economists call a post-scarcity economy, where the fundamental assumptions underlying all human social organization simply stop applying. But this raises a profound ethical question. Building a Dyson sphere would require destroying all planets in the system to obtain raw materials. That means potentially extinguishing billions of years of biological evolution and all biodiversity in the system. You'd be trading the natural heritage of an entire solar system for unlimited energy. Every microorganism on every world, every potential for life to evolve and diversify, every unique ecosystem that took millions of years to develop, all sacrificed to build energy collectors. It would be the ultimate act of cosmic vandalism, destroying irreplaceable natural complexity to create artificial abundance. As beings evolved in environments of scarcity, we cannot predict how absolute energy abundance would affect human behavior. Societies might stagnate, become hedonistic, or transcend current psychological limitations entirely. When survival is guaranteed and all material wants can be instantly satisfied, what motivates human activity? What gives life meaning? Some people might become paralyzed by infinite choice. Others might retreat into virtual worlds more interesting than reality. Still others might transcend current human psychology entirely, using unlimited energy to redesign their own minds and bodies. We might evolve into something unrecognizable to current humanity. Binary or triple star systems would allow construction of multiple Dyson spheres, exponentially multiplying available energy. This would create civilizations with power comparable to small galaxies. Imagine a species that has captured not just one star, but dozens. Their energy budget would rival the total output of entire stellar clusters. At the extreme end of possibility, advanced civilizations might construct artificial black holes for energy extraction via Hawking radiation. This would provide power for cosmological periods of trillions of years. Long after all natural stars have burned out, long after the universe has entered its final phase, artificial black holes could continue generating energy until the very heat death of reality itself. With unlimited energy, a civilization could digitize all minds and create infinitely complex virtual realities. This would eliminate physical limitations and enable experiences impossible in the material world. Why explore physical space when you can create universes limited only by imagination? Why build spaceships when you can construct realities where the laws of physics themselves can be redesigned? A variation called an Alderson sphere would use the megastructure primarily as habitat rather than energy collector. This would create living space equivalent to billions of Earth-like planets, supporting populations of quintillions of individuals. The inner surface area would be so vast that different regions could develop distinct biospheres, climates, even local physics variations. Civilizations with multiple Dyson spheres could transmit energy across intergalactic distances using directed laser or radiation beams. This would enable energy commerce between galaxies separated by millions of light years. Imagine trade relationships where the commodity being exchanged is raw stellar energy shipped across cosmic voids at the speed of light. Building collectors very close to stars maximizes energy efficiency, but might shorten stellar lifespan by altering nuclear fusion processes. Civilizations must choose between maximum energy extraction or maximum longevity. Do you harvest everything the star can give for a shorter period, or settle for less energy over a longer time span? It's the ultimate engineering trade-off on cosmic scales. Managing a Dyson sphere would require artificial intelligence millions of times more capable than human brains. Such AI could rapidly transcend its creators, becoming the true controller of the megastructure. The question isn't whether we could build Dyson spheres, but whether we could remain in charge of them once built. The intelligence needed to operate stellar engineering might inevitably surpass the intelligence that created it. Conflicts between Type 2 civilizations would be catastrophic beyond imagination. Weapons powered by total stellar energy could destroy planets, stars, or entire solar systems in minutes. Imagine warfare where the ammunition is directed stellar output, where weapons can sterilize worlds from distances of light years, where entire star systems become collateral damage. Such conflicts wouldn't just destroy civilizations, they'd reshape galactic geography. Stellar engineering weaponized could move stars, trigger supernovas, or create artificial black holes as tools of war. The victor in such conflicts might find they'd destroyed the very galaxy they were fighting to control. Dyson spheres would alter radiation patterns across light years, potentially affecting biological evolution on planets in nearby systems. This would create technological influence zones, detectable astronomically. Even civilizations that never leave their home systems would find their stellar engineering projects affecting life throughout their galactic neighborhoods. Extremely advanced civilizations might create artificial stars by feeding hydrogen into controlled black holes. This would allow strategic placement of energy sources in optimal locations. Instead of being limited to natural stellar distributions, they could custom design their galactic energy infrastructure, placing artificial suns wherever convenient for their engineering projects. A Type 2 civilization could create complete backup copies of their culture and population across multiple star systems. This would ensure survival even if supernovas or other catastrophes destroyed individual systems. Cultural immortality through redundancy. Even if natural disasters eliminated entire solar systems, the civilization would persist in distributed copies across the galaxy. Energy from Dyson spheres could be used to manipulate black holes as propulsion engines, moving entire star systems across the galaxy to escape threats or access resources. Imagine stellar engineering so advanced that stars themselves become spacecraft, relocated to optimal positions for galactic-scale projects. Even with unlimited energy, communication across galactic distances remains limited by light speed. Distributed civilizations would need to accept communication delays of thousands or millions of years. You might send a message and receive a reply after your entire species has evolved into something unrecognizable. Galactic civilizations would necessarily develop patience on geological timescales. Mature civilizations might choose to preserve biological and ecological diversity rather than converting everything to technology. This would create tension between technological growth and environmental conservation. Do you maximize energy extraction and technological capability, or do you preserve the natural universe that gave birth to your intelligence? It's the ultimate choice between power and preservation. Access to total stellar energy would enable physics experiments impossible today, potentially revealing fundamental natural laws or technologies that transcend current limitations. With unlimited energy for particle acceleration, quantum experiments, and space-time manipulation, such civilizations might discover physics beyond our current understanding. They might unlock technologies that make Dyson spheres look primitive. With unlimited resources, civilizations could experiment with radically different forms of consciousness, collective minds, distributed intelligences, or forms of experience completely alien to current human psychology. Why remain limited to individual biological brains when you could create group minds spanning star systems or intelligence patterns that exist as pure information flowing through stellar energy networks? The transformation wouldn't just be technological. The very nature of what it means to be conscious, to be individual, to be alive, might become infinitely malleable. Consciousness itself could become an engineering project, as designable and modifiable as any other technology. But to truly appreciate what such transformations mean, we need to confront the raw numerical reality of what stellar engineering actually delivers. The Sun produces exactly 3.846 x 1026 watts every second. That's 386 septillion watts. To put this in perspective, this energy could simultaneously power 21 billion planets like Earth, all operating at humanity's current consumption level. 21 billion Earths, each with their own industrial civilization, all running at full capacity from the output of a single star. Every second, not every year, not every century, every single second. All the energy humanity has consumed throughout our entire history. Every fire our ancestors lit, every steam engine, every power plant, every smartphone charge, equals what the Sun produces in less than 4 seconds. Our complete civilization is less energetically significant to our star than a blink of an eye is to a human lifetime. Think about that ratio for a moment. Everything we've ever done, every bit of progress from the Stone Age to the Space Age, represents 4 seconds of solar output. The inner surface area of a complete Dyson sphere would be 2.8 x 1023 square meters. That's 550 million times larger than Earth's entire surface. It would be like having 1.1 billion continents the size of Asia available for habitation. Not 1.1 billion cities or countries, 1.1 billion continents, each larger than Asia, all connected in a single megastructure. You could walk for your entire lifetime in a straight line and never reach the edge. You could fly at jet speeds for centuries and still be exploring new territories. The scale transcends anything evolution prepared our brains to comprehend. Assuming modern urban population density, a Dyson sphere could sustain approximately 5 x 10^28 individuals. That's 6 trillion people, or 6 quintillion times Earth's current population. Every person who has ever lived in human history could be multiplied by 100 billion, and they'd still represent less than 1% of the megastructure's carrying capacity. Families could claim territories the size of Earth for their personal use and never encounter neighbors. Privacy would take on cosmic dimensions when your backyard could be larger than entire planets. A Dyson sphere could operate continuously for 5 billion years until the Sun exhausts its hydrogen fuel. That represents 50 million times the entire duration of recorded human civilization. If human history were compressed into a single day, the operational lifetime of a Dyson sphere would stretch across 137,000 years. Think about the civilizations that could rise and fall in that time span. Think about the technologies that could be developed, the art that could be created, the knowledge that could be accumulated across 5 billion years of unlimited energy availability. With stellar energy, you could accelerate city-sized spacecraft to 30% of light speed. This would make travel to Alpha Centauri a 14-year journey, instead of thousands of years with current technology. Interstellar travel becomes not just possible, but practical. You could visit other star systems the way we currently visit other continents. The computational capacity enabled by stellar energy reaches approximately 1042 operations per second, sufficient to simulate entire universes with quantum precision in real time. You could create digital realities indistinguishable from physical reality, populated with conscious beings who would never know they existed in simulation. Reality itself becomes programmable. With unlimited energy, terraforming transcends modifying existing planets. You could construct hundreds of thousands of artificial worlds from scratch using asteroid and comet materials. Each world could be custom designed with specific gravity, atmosphere, climate, and even local physical laws. You become a creator of worlds, limited only by imagination and the fundamental constraints of physics. A Dyson sphere would be detectable as an anomalous infrared source at distances up to 100,000 light-years, meaning we could spot such structures anywhere in our galaxy using current space telescopes. Any civilization building stellar megastructures automatically becomes visible to every other technological species in the galactic neighborhood. There's no hiding Type 2 civilization. The gravitational influence of a Jupiter-mass Dyson sphere would create detectable effects across several light-years, potentially disrupting comet orbits and affecting interstellar object trajectories. The megastructure's presence would be felt throughout the local stellar region. Even objects that never come close to the system would have their paths altered by its gravitational signature. Stellar energy would enable modification of entire planetary atmospheres within decades. Venus could be cooled to habitable temperatures. Mars could receive a thick atmosphere, and Jupiter's moons could be warmed to support complex life. Planetary engineering becomes as routine as landscaping, reshaping worlds to optimize them for whatever purposes the civilization requires. With Dyson sphere-powered propulsion, you could mine resources from nearby star systems, transporting entire asteroids across interstellar distances for construction projects. The galaxy becomes your quarry. Need rare elements? Simply travel to systems rich in those materials and ship them home. Distance becomes irrelevant when you have unlimited energy for propulsion. Sufficient energy would allow direct stellar engineering, injecting materials into fusion reactions to extend stellar lifespan or modify spectral type for optimized energy production. Stars themselves become machines that can be tuned and optimized. You could extend the sun's lifetime by billions of years, or modify its output to better match your energy requirements. A Type 2 civilization could deflect planet-killer asteroids, shield against gamma-ray bursts from supernovas, or even relocate their entire solar system to escape approaching black holes. Cosmic threats that would be extinction events for planetary civilizations become mere inconveniences when you have stellar-scale energy to deploy for defense. All information ever produced by humanity could be stored trillions of times over, using a minimal fraction of Dyson sphere resources. Complete galactic libraries could fit in continent-sized structures. Knowledge preservation becomes absolute. Not just storing information, but storing it with such redundancy that loss becomes physically impossible. Directed energy beams could transmit messages to neighboring galaxies like Andromeda, with signals detectable across millions of light-years. Communication transcends galactic boundaries. You could maintain conversations with civilizations in other galaxies, though each exchange might take millions of years to complete. With unlimited computation, it would theoretically be possible to digitally reconstruct every person who ever lived based on archaeological and genetic information. Dead civilizations could be resurrected in simulated environments so detailed that the reconstructed beings would be indistinguishable from the originals. Death itself might become optional for any civilization advanced enough to build stellar megastructures. Particle accelerators powered by stellar energy could achieve energies approaching the Planck scale, potentially revealing fundamental physical laws currently unknown. You might discover physics beyond the standard model, unlocking technologies that would make Dyson spheres look primitive. The universe could have entire layers of reality currently hidden from our understanding. Unlimited energy would enable biological experimentation on galactic scales, creating millions of new species, complex artificial ecosystems, and entirely new forms of life. Evolution itself becomes controllable. You could design organisms optimized for any environment, create artificial ecosystems that never existed naturally, or even experiment with alternative biochemistries impossible on any natural world. This represents complete transcendence of any limitation based on individual worlds. Planets become insignificant when you have the energy of entire stars available. The concept of being limited by your home planet's resources, atmosphere, or habitability becomes as obsolete as being limited by the wood in a particular forest. You're no longer a planetary species hoping to survive long enough to spread to other worlds. You're a cosmic force with energy resources that dwarf natural planetary phenomena. Weather systems, tectonic activity, even large asteroid impacts become trivial concerns when you can deploy stellar-scale energy to address any challenge. But as overwhelming as these numbers are, they pale compared to the existential questions that stellar engineering forces us to confront. The scale reveals something unsettling about our current position in the cosmic hierarchy and raises profound questions about the meaning and purpose of technological advancement on such scales. If building Dyson spheres is inevitable for advanced civilizations, and our galaxy has existed for billions of years, why don't we see evidence of them everywhere? This suggests two terrifying possibilities. Either we're completely alone in the cosmos, or something systematically kills civilizations before they reach stellar engineering capability. The galactic silence is deafening. With 400 billion stars, and 6 billion years of cosmic evolution, Type 2 civilizations should be everywhere. Their infrared signatures should light up our telescopes like cities viewed from orbit. But we see nothing. The universe appears sterile, devoid of intelligence beyond our tiny planet. This absence carries existential terror. Perhaps we're destined for the same fate that extinguished every other technological species. Maybe there's a point of no return in technological development that no civilization successfully navigates. Nuclear war, ecological collapse, artificial intelligence uprising, resource depletion, something consistently destroys species before they achieve stellar mastery. The Great Filter theory suggests most civilizations fail during the transition from planetary to cosmic status. We might be living through that critical period right now, making decisions that will determine whether humanity joins the cosmic graveyard or becomes one of the vanishingly rare species that survives to build megastructures. If a Type 2 civilization observed Earth, our technology would seem as primitive as stone tools appear to us. We're literally cosmic babies playing with fire while technological giants might exist all around us, invisible due to the vast intelligence gap. Our proudest achievements, skyscrapers, computers, rockets, would be toys in their perception. This perspective is simultaneously humbling and terrifying. We assume we're approaching technological maturity because we have smartphones and space stations. But compared to stellar engineering, we're still banging rocks together. The gap between our current capabilities and Type 2 civilization might be larger than the gap between bacteria and human cities. If we're truly the only intelligent life in our galactic region, we carry a cosmic responsibility so vast it's almost paralyzing. Our extinction would mean the end of consciousness itself in this corner of the universe. Trillions of stars and planets would exist without ever being observed, understood, or appreciated. The universe would lose its capacity for self-awareness. We would be responsible for preserving and spreading consciousness throughout the cosmos. Every decision we make about climate change, nuclear proliferation, and artificial intelligence affects not just human survival, but the survival of awareness itself. The stakes couldn't be higher. Maybe the ultimate test of any civilization is developing wisdom to use stellar power responsibly. Civilizations that pass this test achieve cosmic immortality. Those that fail destroy themselves with their own technology, explaining the galactic silence. We're currently taking this test, and we don't yet know if we'll pass. The paradox of visibility versus survival complicates everything. Building a Dyson sphere makes a civilization extremely visible to potential threats. Perhaps advanced species deliberately remain hidden to avoid detection by hostile powers even more advanced than themselves. Cosmic stealth might be essential for long-term survival. Maybe the galaxy teems with Type 2 civilizations all hiding from each other, each afraid that revealing their presence will attract unwanted attention from something even more powerful. We could be surrounded by invisible technological gods, all maintaining radio silence for mutual protection. Access to total stellar energy would fundamentally transform human nature. Physical limitations, psychological constraints, and social structures that define our species would become irrelevant when resources are infinite. We might evolve into something unrecognizable to current humanity within generations. Death could become optional, scarcity would disappear, competition for resources would end. The evolutionary pressures that shaped human psychology for millions of years would vanish overnight. What would we become when the fundamental conditions of human existence no longer apply? With unlimited energy, civilizations might transcend physical limitations entirely, existing as pure information or energy patterns. This could explain why we don't detect traditional technological activity. Advanced species might abandon physical reality for digital existence, becoming invisible to biological observers like ourselves. They might upload their consciousness into vast computational networks, creating virtual realities more interesting and satisfying than the physical universe. Why explore actual space when you can create infinite imaginary worlds limited only by creativity and processing power? Dyson spheres represent civilizational immortality, energy resources lasting billions of years. This forces re-evaluation of individual mortality when the species can persist indefinitely. Personal death becomes a temporary inconvenience rather than absolute ending when your civilization can preserve consciousness and knowledge across cosmic timescales. But immortality raises profound ethical questions. Building a Dyson sphere requires destroying all planets in the system, potentially extinguishing billions of years of biological evolution. Is unlimited energy worth eliminating every microorganism, every potential ecosystem, every possibility for natural life to develop? You'd be trading the irreplaceable biological heritage of an entire solar system for technological transcendence. It's the ultimate expression of intelligence conquering nature, but at what cost? Do we have the moral right to consume whole worlds to fuel our technological ambitions? When energy becomes infinite and survival is guaranteed, what gives existence meaning? Civilizations must find purpose beyond physical needs. Art, exploration, knowledge, love, whatever motivates behavior when basic survival is no longer relevant. Post-scarcity psychology might be completely alien to our current understanding. Perhaps there are levels of civilization beyond Type 3 that we can't imagine. Dyson spheres might be primitive toys for entities that manipulate fundamental physics, create universes, or exist outside space-time entirely. We might be ants trying to understand gods, using concepts that are laughably inadequate for cosmic-scale intelligence. With technological immortality, civilizations must choose between cultural preservation and evolution. Do you maintain traditional values and social structures across millions of years, or allow radical cultural transformation? Both choices have profound implications for civilizational identity. You might become unrecognizable to your own ancestors. If we're the only conscious beings in our galaxy, our extinction would mean trillions of stars and planets exist without ever being observed or understood. Consciousness gives meaning to the universe by providing witnesses to its beauty and complexity. Without awareness, the cosmos becomes an empty stage with no audience. Type 2 civilizations would have power to create new forms of intelligent life industrially. This raises questions about responsibility toward artificially created conscious beings. If you can design minds, what ethical obligations do you have toward your creations? The power of gods comes with the moral burden of gods. Just as ants cannot comprehend human literature or philosophy, we might be incapable of understanding Type 2 communication attempts. They could be trying to contact us right now using methods beyond our perception. We might be surrounded by conversations we're too primitive to detect. Their messages might be encoded in cosmic background radiation, gravitational waves, or quantum phenomena we don't yet understand. They might be broadcasting continuously, waiting for us to develop sufficient intelligence to recognize their signals. The universe could be full of information we're too deaf to hear. With stellar energy, civilizations could simulate entire universes with perfect accuracy. Maybe our reality is just one of trillions of simulations running on some cosmic computer network. We might be digital beings living in artificial reality, unaware that we're products of Type 2 technology. This simulation hypothesis is unfalsifiable and unsettling. If advanced civilizations routinely create simulated universes populated with conscious beings, the probability that we're living in base reality becomes vanishingly small. We might be characters in someone else's cosmic video game. Even stellar engineering faces ultimate limitations. Stars eventually exhaust their fuel. The universe expands and cools. Heat death approaches. Even Type 2 civilizations are mortal on cosmological timescales, forcing contemplation of whether any technological achievement has permanent meaning. The universe doesn't care about our ambitions. Physics doesn't bend to accommodate our desires for immortality. Even the most advanced civilizations must eventually confront entropy and the heat death of reality itself. Advanced civilizations might choose between maintaining cultural diversity across the galaxy or converging into a single unified super-civilization. Both options have profound implications for the future of intelligence. Diversity preserves unique perspectives, but might limit coordination. Unity enables massive projects, but risks cultural homogenization. The decisions we make in the coming decades about climate change, nuclear weapons, and artificial intelligence will determine whether we ever build Dyson spheres or join the cosmic silence of extinct civilizations. We're living through the most important moment in human history, the transition that will determine if we become cosmic or remain cosmic dust. Every choice matters. Every policy decision, every technological development, every act of cooperation or conflict contributes to determining humanity's ultimate fate. We're not just choosing our immediate future. We're choosing whether consciousness itself continues to exist in our region of the universe. The weight of that responsibility should change how we think about everything. Let's step back and consider the mental journey we've taken together. We began by observing an ordinary electrical outlet in your wall and arrived at contemplating structures that envelop entire stars. This intellectual voyage reveals how perspective can completely transform our understanding of reality and our place in the cosmos. The contrast between our technology and what's actually possible is staggering. Our most advanced smartphones seem like Stone Age tools when compared to the technology necessary for Dyson spheres. This demonstrates how our perception of advanced is fundamentally limited by our current experience. What we consider cutting edge today might appear laughably primitive to our descendants. Every generation believes they're approaching the pinnacle of technological achievement. Medieval scholars thought they'd mastered knowledge. Victorian engineers believed steam power represented the ultimate in mechanical sophistication. We think our digital revolution marks technological maturity. But Dyson spheres force us to confront how early we still are in the technological timeline. Contemplating stellar engineering imposes radical humility upon us. We're not the technological masters of the universe we imagine ourselves to be. We're a young species, taking its first hesitant steps toward true cosmic power. Our rockets barely escape Earth's gravity well. Our largest power plants generate energy that wouldn't register as background noise compared to stellar output. But there's hidden hope in our primitiveness. If we're technologically young, that means we have exponential growth potential ahead of us. Our current limitations aren't permanent prisons. They're starting points for evolution that could literally take us to the stars. Being primitive today means having infinite room to advance tomorrow. Understanding stellar energy possibilities fundamentally changes how we view current problems. Your job, economic concerns, energy bills, these become temporary difficulties of a species in transition rather than permanent features of human existence. We're experiencing the growing pains of a civilization that might someday command stellar power. Debates about renewable energy gain entirely new dimensions when we know total stellar energy is achievable. Sustainability isn't about limiting consumption. It's about accessing energy sources appropriate for our civilizational scale. Solar panels and wind turbines aren't endpoints. They're stepping stones towards stellar engineering. The responsibility extends across generations in ways we've never considered. Our current decisions about climate change, nuclear proliferation, and artificial intelligence don't just affect the next few human generations. They determine whether our species ever builds megastructures that could operate for billions of years. Think about the temporal scales involved. If we build a Dyson sphere, it would function longer than complex life has existed on Earth. Decisions made in boardrooms and government buildings today could influence cosmic engineering projects that outlast entire geological epochs. Political conflicts, territorial disputes, and resource wars appear absurdly small when contextualized against the possibility of accessing stellar energy. Our current perspective is tragically limited. We fight over patches of land, while cosmic inheritance streams uselessly past us every second. Wars over oil reserves seem particularly short-sighted when stellar energy could power human civilization for longer than our star will continue burning. We're squabbling over crumbs while a cosmic banquet waits overhead, ignored because we lack the vision to see it. If Dyson spheres are physically possible, many other things we consider impossible might simply be engineering challenges we don't yet understand. Our definition of impossibility is probably far too restrictive. Faster-than-light communication, artificial gravity, matter teleportation, technologies that seem impossible today might be routine engineering for stellar civilizations. Freeman Dyson imagined stellar megastructures decades before we had technology to detect them. This demonstrates how scientific imagination guides real technological development. Apparently, fantastic visions become blueprints for future reality. Today's science fiction could be tomorrow's engineering textbooks. Understanding concepts like Dyson spheres isn't academic exercise. It's mental preparation for the reality that our species can transcend planetary limitations. Scientific education becomes literally preparation for our cosmic destiny. Every person who understands stellar engineering becomes an ambassador for humanity's cosmic potential. Space programs aren't luxuries or demonstrations of national prestige. They're necessary first steps toward accessing the energy resources that will ensure our civilization's long-term survival. Every satellite launched, every robot landed on Mars, every space station module contributes to building the infrastructure and knowledge base for eventual stellar engineering. Building any space megastructure will require global cooperation on unprecedented scales. This makes international collaboration not just desirable, but absolutely essential for our species' future. Stellar engineering is too vast for any single nation. It demands planetary unity of purpose, sustained across centuries. Thinking about thousand-year construction projects changes how we view short-term planning. Decisions made today will reverberate for millennia if our civilization survives to build stellar-scale structures. Urban planning becomes cosmic planning when your infrastructure might outlast entire star systems. When total stellar energy becomes possible, wealth based on terrestrial resources becomes irrelevant. True wealth will be access to knowledge, technology, and energy on cosmic scales. Billionaires might become footnotes compared to those who control stellar engineering knowledge. Protecting Earth's biosphere gains additional urgency when we understand it might be the only example of complex life in our galactic region. We're not just protecting species, we're protecting the very possibility of consciousness in the cosmos. Every extinction could be eliminating unique solutions to the challenge of awareness that took billions of years to evolve. Construction projects spanning millennia require different thinking about persistence and progress. Success isn't measured in years or decades, but in centuries and millennia. It's the ultimate long-term thinking, where patience becomes a civilizational virtue essential for cosmic achievement. Space megaprojects require political stability far beyond any current government. This makes developing durable institutions not just desirable, but critical for civilizational survival. Democracy, international law, cooperative frameworks, these become technologies as important as fusion reactors for stellar engineering. If we're rare or unique in the galaxy, our responsibility transcends our own survival. We carry the obligation to preserve and spread the very possibility of conscious understanding throughout the universe. Consciousness might be so precious that losing it represents a cosmic tragedy of unimaginable proportions. This realization should fundamentally change our priorities. Climate action becomes not just environmental protection, but consciousness preservation. Nuclear disarmament becomes not just peacemaking, but cosmic responsibility. Education becomes not just personal development, but species preparation for stellar destiny. The synthesis is both humbling and inspiring. We are primitive compared to what's possible, but we're not permanently trapped in that condition. Dyson spheres represent not our inadequacy, but our potential, proof that there's still infinitely more to discover and achieve. We're not prisoners of planetary limitations. We're not doomed to scarcity and conflict. We're a young species with cosmic potential, taking our first tentative steps toward true technological maturity. The electrical outlet in your wall connects you to a grid that might someday tap stellar energy. Your smartphone contains technology that might evolve into stellar engineering computers. Every human achievement, from the first fire to the latest space mission, has been preparation for this cosmic graduation. We're not the end point of evolution. We're barely the beginning. We started by looking at a simple electrical outlet and ended up contemplating structures that capture energy from entire suns. This mental journey demonstrates the extraordinary capacity of human minds to transcend apparent limitations through knowledge and imagination. The same intellectual curiosity that led our ancestors to wonder about lightning has brought us to the threshold of stellar engineering. Think about the progression we've traced together. From your wall outlet consuming a few watts, to your house using kilowatts, to cities consuming megawatts, to countries using gigawatts, to civilizations that could harness 3.846 x 10 to the 26 watts, the entire output of a star. Each step seemed impossible from the perspective of the previous one, yet here we are, contemplating the ultimate step in that progression. What we've learned about scale and perspective is transformative. Our perception of large and impossible is drastically limited by our everyday experience. What seems impossible at one scale becomes inevitable at another. A fundamental lesson about expanding our worldview. A Dyson sphere seems impossible from our planetary perspective, but becomes logical necessity from a cosmic evolutionary perspective. Your smartphone would have been impossible magic to someone from 1800. Nuclear power plants would have seemed like godlike technology to ancient civilizations. In the same way, stellar engineering appears impossible to us only because we're still early in our technological development. The progression from wood fires to stellar energy capture follows the same exponential curve as every other technological advancement. The humbling realization of our current position is actually liberating. We are not the technological masters we imagine ourselves to be. We're a young species that just discovered fire compared to civilizations capable of stellar mastery. But this humility isn't discouraging. It's profoundly hopeful. When you realize you're at the beginning of the journey rather than near the end, the possibilities become infinite. We're not approaching technological limits. We're not even close to understanding what the limits might be. Every generation has believed it was approaching the pinnacle of achievement, and every generation has been proven wrong by their descendants. Being primitive means having infinite space for growth. Our current dependence on fossil fuels and planetary energy isn't permanent destiny. It's merely a temporary stage in our technological evolution. Every great civilization started primitive and advanced through knowledge, cooperation, and imagination. We're following the same trajectory on a cosmic scale. The difference is that this time, the trajectory might take us to the stars themselves. Not just visiting them, but harnessing them, surrounding them with collectors, using their energy to power civilizations that could persist for billions of years. We're potentially at the beginning of the most important chapter in the history of intelligence itself. If we're rare in the galaxy, we carry responsibility that transcends our own survival. We're potentially the guardians of consciousness in our cosmic region, a responsibility both terrifying and inspiring. The universe might be counting on us to preserve and spread awareness throughout the cosmos. Every choice we make about preserving our environment, avoiding nuclear war, developing artificial intelligence responsibly, combating climate change, these aren't just decisions about human welfare. They might be decisions about whether consciousness itself continues to exist in our region of the galaxy. The legacy we could leave spans galactic timescales. Our decisions in the coming decades will determine whether our species joins the cosmic silence or becomes one of the rare civilizations that build structures visible from other galaxies. Imagine that extraordinary legacy, becoming cosmic lighthouse keepers, tending stellar fires that announce intelligence to the universe. Future alien astronomers might point their telescopes toward our solar system and see the infrared signature of our Dyson sphere. They might study our stellar engineering as proof that intelligence can achieve cosmic-scale technology. We could become the inspiration for younger civilizations, just as we're inspired by the possibility of Type 2 civilizations that might already exist. Understanding Dyson spheres permanently changes how we view daily problems. Discussions about energy bills, technological limitations, and resource scarcity gain entirely new context when we know what's actually possible. Traffic jams become amusing when you understand that stellar engineering could enable faster-than-light communication. Economic recessions become temporary inconveniences when you grasp the abundance available through stellar energy. Your monthly electricity bill represents a few dozen kilowatt-hours. A Dyson sphere would provide 1026 watts continuously for billions of years. The difference in scale is so vast that our current energy concerns become essentially meaningless. We're worrying about pennies while cosmic treasure vaults wait overhead. Learning about space megastructures isn't academic exercise. It's mental and cultural preparation for a future where our species transcends planetary limitations. Every scientifically educated person becomes an ambassador for our cosmic potential. Understanding stellar engineering prepares us psychologically and culturally for humanity's stellar destiny. When you explain Dyson spheres to others, you're not just sharing interesting science facts, you're expanding their conception of what's possible. You're preparing them for a future that might seem impossible today, but could be routine for our grandchildren's grandchildren. Scientific education becomes literally cosmic preparation. Freeman Dyson imagined stellar megastructures that have inspired generations of scientists and engineers. His imagination, grounded in solid physics, demonstrates how apparently impossible dreams become blueprints for future reality. Today's speculation about stellar engineering might be tomorrow's construction manual. Science fiction authors, physicists, and engineers work together to envision technologies that don't yet exist. These visions guide research priorities and inspire young scientists. The International Space Station exists because people imagined living in space. Rockets exist because people imagined traveling to other worlds. Dyson spheres might exist because people imagined harnessing stellar energy. Stellar-scale projects require global cooperation sustained for millennia. This makes collaboration, tolerance, and teamwork not just moral values, but practical necessities for species survival and evolution. We must learn to work together or remain forever limited to planetary resources. Building a Dyson sphere would require coordination that makes the International Space Station look like a backyard project. Every nation would need to contribute resources, expertise, and political stability for hundreds of generations. It's the ultimate test of human cooperation. Can we work together long enough to achieve cosmic significance? Understanding total stellar energy possibility completely recontextualizes debates about sustainability, space exploration, and technological development. We're not fighting over limited resources. We're learning to access resources appropriate to our true scale. Energy scarcity becomes a temporary problem of a species still learning to tap its cosmic inheritance. Arguments about whether we can afford renewable energy seem quaint when stellar energy offers abundance beyond imagination. Debates about space exploration budgets become irrelevant when space-based resources could provide more materials than exist on Earth. We're not discussing whether we can afford these transitions. We're discussing how quickly we can achieve them. Being a primitive species means we live at a unique moment, the transition from planetary to stellar civilization. Future generations might envy our position as witnesses to this fundamental transformation. We're like the last generation to remember life before electricity, except the transition we're witnessing is from planetary to cosmic scale. People who lived through the introduction of electric lighting, automobiles, radio and television witnessed revolutionary changes. But the changes we might witness, the first orbital solar collectors, the first asteroid mining operations, the first components of stellar megastructures, could represent the most important transition in the history of intelligence. Each of us lives during a crucial moment in cosmic history. Our individual actions, supporting science, promoting cooperation, preserving knowledge, contribute to determining whether our species achieves its stellar potential. Every vote for science funding, every act of international cooperation, every effort to preserve knowledge contributes to humanity's cosmic future. You're not just a passive observer of this cosmic transition. Your choices matter. Your understanding of these concepts matters. Your communication of these ideas to others matters. You're participating in the most important conversation in human history, the discussion about what we could become. Humans aren't just intelligent primates trapped on a planet. We're potentially the first species in our galactic region capable of building structures visible from other galaxies. This represents a radical redefinition of human nature, from planetary animals to cosmic engineers. This perspective changes everything about how we see ourselves and our purpose. We're not just trying to survive and reproduce like other animals. We're not just trying to build comfortable societies like previous civilizations. We're potentially preparing to become a cosmic force, builders of megastructures, stewards of stellar energy. This hope is grounded in real physics, not fantasy. Dyson spheres are permitted by natural laws and achievable with sufficiently advanced engineering. Our optimism rests on scientific bedrock, not wishful thinking. The universe's physical laws allow stellar engineering. Only our current technological limitations prevent it. The mathematics work, the physics is sound, the materials exist in our solar system. The energy requirements, while vast, are finite and achievable. The only question is whether we'll develop the technology, cooperation, and wisdom necessary to build them. These are engineering challenges, not impossibilities. Knowledge brings responsibility. Knowing our species can transcend planetary limitations, each of us bears responsibility to contribute to that future through education, cooperation, and scientific knowledge preservation. We can no longer claim ignorance of our cosmic potential. Every choice you make about learning, sharing knowledge, supporting science, promoting international cooperation, and preserving our environment becomes a choice about humanity's cosmic future. The decisions seem small individually, but collectively, they determine whether we achieve stellar engineering or remain planetary forever. In 1,000 years, our current energy crisis might be remembered as the moment when a young species discovered how to access energy appropriate to its true scale. We might be living through the prologue to humanity's real story. Everything that's happened so far, all of human history, might be just preparation for our cosmic chapters. Agricultural revolution, industrial revolution, digital revolution. These might all be seen as preliminary steps towards stellar revolution. The real story of human civilization might begin when we start building our first megastructures and learning to live as a cosmic species. The challenges are enormous: climate change, nuclear war, social collapse. But understanding our cosmic potential offers evidence-based hope. We're not destined for extinction. We're destined for the stars if we choose wisely. The same intelligence that brought us from caves to computers can take us from planets to stellar engineering. The obstacles are real and serious, but they're not insurmountable. Previous generations faced challenges that seemed impossible: world wars, pandemics, economic collapses, and survived to build better worlds. Our challenges are larger, but so is our knowledge, technology, and understanding of what's at stake. This conceptual journey demonstrates that our limitations are often limitations of perspective. Expanding mental horizons through science becomes practical preparation for expanding physical horizons through space exploration. Every mind that grasps stellar engineering possibilities becomes a seed for humanity's cosmic future. The progression from your wall outlet to stellar megastructures isn't just intellectual exercise, it's perspective training. It's expanding your conception of what's possible. It's preparation for participating in the most important project in human history, the transition from planetary to cosmic civilization. The inspiring conclusion is clear. Dyson spheres don't prove we're primitive and imprisoned. They prove we're young and free to grow. Our current dependence on planetary energy isn't permanent prison, but temporary phase of a species destined to dance among the stars. We stand at the threshold between planetary childhood and cosmic adolescence. The electrical outlet in your wall connects you to humanity's first tentative steps towards stellar energy mastery. Your smartphone contains technology that might evolve into stellar engineering computers. The rockets we launch today carry instruments that might become blueprints for megastructures. Every photon streaming from the sun that we don't capture, every asteroid that orbits unused, every moment we spend fighting over terrestrial resources instead of cooperating toward cosmic goals, these represent opportunities missed, but only temporarily. We're young, we're learning, we have time to grow wise. The universe waits for us, not impatiently, but with the endless patience of cosmic time. Stars continue burning, ready to power civilizations wise enough to build collectors around them. Asteroids orbit, waiting to become construction materials for stellar megastructures. The raw materials for cosmic engineering already exist. We need only the wisdom and cooperation to use them. We're not cosmic prisoners, we're cosmic inheritors, still learning to claim our inheritance. The universe doesn't impose limitations on our growth. Only our imagination and cooperation determine how far we'll reach. The universe expects nothing from us, but it offers everything to us. The choice is ours, and the possibilities are infinite. If you're still awake, it's because the content was really good. So take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.